Over the last few weeks, we've been looking a lot at exponential equations and we've been dealing with logarithms. Today we're going to be putting those together. We're going to be solving exponential equations, and you're going to see that we're going to end up needing to use some logarithms along the way. As we go through this, of course, be writing down the examples as we go. If you find that I'm going a little bit too fast, you can always pause the recording, remember, so you can be catching up. You can rewind it to catch something I said again. Make sure you really understand what all's happening with doing these. All right, so if I'm going to be solving this particular problem, the first thing I want you to notice is that x is in our exponent. That means I can't just do a lot of the things that I would have known before this year. I have to find some way to rewrite this equation, some way to rewrite it and get that x out of the exponent. That is the entire reason why logarithms exist. Logarithms exist in order to solve for an exponent. So I switch this into logarithmic form. Now that it's in log form, I now need to calculate what this equals. So this means I go back now to the change of base formula, where I'm going to do log of 80 divided by log of 8. And I put that in the calculator, and I end up getting an answer here of about 2.11. Yeah, I'm going ahead and rounding it to the nearest hundredth here. And so then this is my final answer. That's what I was looking for, that x equals about 2.11 here. And that's basically the whole idea that we're doing today. It's just that we're going to be seeing this come up in different contexts and in more complicated questions. This was a nice simple example. This one doesn't look nearly as simple, but it's actually just as doable because you already know a lot of the math skills. We are going to need to be solving again for an exponent in this case, which means yes, a logarithm will be involved. Whenever you're dealing with this sort of a case, you want to get that exponential part of your equation by itself first. So I'm trying to isolate that 3 to the power of x minus 1, which means I have to get rid of the 2 and I have to get rid of the minus 8. Well, between those two, I always want to go backwards through the order of operations since I am solving the equation, so I'm undoing it. So the first thing I'm going to want to do is move that minus 8 out of the left side and into the right side. So I add 8 to both sides, and now I can get rid of the 2. So now I'm going to go ahead and divide both sides by 2. And now I have the exponential part by itself. Once I have just a number to the power of something involving x, yes, I know there's that 1 up there, but it's got to stay with it because it's still in the exponent. Now that I'm at this point, I turn it into a logarithm. So, rewrite it into logarithmic form. And so you'll notice that the entire exponent, the whole x minus 1, is over here that's equal to the logarithm. And then on the other side, I now have log base 3 of 64. That's one that I'm going to have to break out the calculator to actually solve. So we do log of 64 divided by log of 3, and go ahead and put that in your calculator, and you should end up with an answer of about 3.78. Now this is actually a big long decimal that goes on and on and on. I'm keeping that number showing on my calculator right now. I'm not going to actually write down the rounded number until we're all done. And I'm not going to press clear on my calculator until I'm all done. All right, last step. I'm still trying to get what x equals. All I got to do is get rid of that 1 now. So I'm going to add 1 to both sides. And when I do that, I then can round it because it's just plain old x over here. And so in this case, x equals about 4.79. And you'll notice that it's a 9 because of the numbers that I didn't write down over here. I just wrote down the 3 dots just to remind myself, yes, there's more to this. The only reason I'm really writing this number down is just to keep track of which number I'm working with at what time. But then it's at the final answer that I then do that rounding. All right, and so this one's done. And if you can work out this problem, then you're going to be able to do any of the basic solving exponentials types of equations that you're going to be seeing. But we have been seeing exponentials come up in some other contexts as well. For instance, we've been seeing them come up in the context of like a compounding interest equation. So we're going to be doing this sort of a problem. Read through this problem, probably want to pause it, and then we'll work it through here together. All right, so the first thing I want to do is I want to write the exponential equation for this. All right, so this is going to be a of t equals an equation in this form, the p times 1 plus r to the t. And so in this case then, my p-value, my principal, my starting value, all those mean the same thing, is 150. And that's 1 plus r. Here my rate is 4%. Remember, turn your percent into a decimal. So 4% becomes 0.04. I divided it by 100 to get that. And then that's to the power of t. Because I don't know what t is yet. In fact, that's what I'm going to be trying to figure out. So if I have this equation of a of t equals 150 times 1.04 to the t, right now I have two variables in there. I have the a in there still, and I have the t in there still. Well, if I'm trying to solve for t, that means I should know what a is. And in fact, I do. Because we're being asked how long will it take for the bond to be worth at least $350. That's the final amount. And so I'm going to take that $350 then and plug it in for the a of t. Now notice it goes in for the whole a of t. We do not end up with something like 350 parentheses t. Remember, a of t is all one unit of the equation. That all means one thing. It's the value of a at t. This would mean that we're actually doing a times t, which is not the same thing. So it is not that. So just want to keep that part straight with using function notation properly. All right, but back to our original problem here. We now have an equation written out to represent this problem. Now we can solve it. And based on what we've seen today on how we could solve it, hopefully you can already be able to do that on your own. In fact, trying it on your own before we go through it here together would be a great idea. So I want to get the exponential part by itself. That means I got to get rid of the 150. So I divide both sides by 150. Now since that gave me 2.3 repeating, I went ahead and just wrote it down that way, 2.3 with the line over it, so I keep track of it. But again, I'm keeping that whole number showing on my calculator as I do this. All right, now that I have the exponential part by itself over here, I now want to be able to solve it for the exponent, which means turning it into a logarithm. Anytime you're solving for an exponent, you are writing it as a logarithm. And so, there's my logarithm. Now some of you I know are looking at that and saying, that looks scary. There's decimals everywhere. That's okay. In fact, that's pretty common with these. But it's okay, we still proceed with calculating it the same way we always would. And that is to use the change of base formula, which is the log of the 2.3 repeating over log of my base 1.04. Now remember how I said we don't clear that 2.3 repeating off our calculator? Notice when you go to do this calculation, that's actually very useful then, because that 2.3 repeating is still showing on your calculator. So you can go ahead and just do log of that number. You don't have to type it in again. Just use log of that number and then divide it by the log of the 1.04. When you do that, you get an answer here of about 21.60. Now, in this kind of a case, we're looking to say, okay, when will we have at least $350? And that word at least there would suggest to us, okay, maybe go ahead and just round it up to the nearest year. And if we did that, that would give us 22 years. And so, depending on what the question is asking for, like if you're doing this on a WAMAP or something, if it says give your answer out to the nearest hundredth, enter that number. If it says to the nearest year, give me that number. Now, a little side note you can see over here. A lot of times when I see people do this problem, I'll see them actually clear their calculators and just type in 2.3 when they're doing this part of the calculation. I actually see that quite a bit, which is why I keep re-emphasizing this whole idea about not doing that. And I'm trying to make sure that we build a habit. If you had used 2.3 instead of the 2.3 repeating, you would have gotten an answer here of 21.24 instead of the 21.6. Now, that's not a huge difference in terms of like it's not exactly like 10 years difference, but it is a fairly significant difference. In fact, if you were just rounding to the nearest year, that might well be the difference between you thinking it's 21 years and 22 years. And so those sorts of things can make a big difference. So just be very, very careful about it, especially because if you were doing this on WAMAP and it was asking you for the answer out to the nearest hundredth, this answer over here with the 21.24, that would definitely have been off. That would have been marked incorrect, and it would have just been because of rounding. You knew how to do it, but it was just rounding in the middle that threw you off. And we don't want that to be the problem. We have to be precise in math, and so stay precise throughout the entire process.